in this session we are actually going to find out the time response of a first order system. So before going to find the time response of first order system, let's see what is the order of a system. So what do we mean by the order of a system? We can actually represent the transfer function of a system T of s as a ratio of a numerator polynomial, say P of s, to the denominator polynomial Q of s. So we can write T of s is equal to P of s by Q of s. The same is equal to b0 s raised to m plus b1 s raised to m minus 1 plus etc. up to bm minus 1 s plus bm divided by the denominator polynomial Q of s can be written as a0 s raised to n plus a1 s raised to n minus 1 plus etc. up to an minus 1 s plus an. Okay, so here the order of the system is actually given by the maximum power of s in the denominator polynomial. So here if we look at this particular expression, we can see that the denominator polynomial is this a0 s raised to n plus a1 s raised to n minus 1 plus etc. up to a n minus 1 s plus a. So that is the denominator polynomial. So the maximum power of s in this denominator polynomial gives the order of this particular system. So here we can see like the maximum power of s in the denominator polynomial is n. So here the order of this system will be n. Okay. And if the value of n is equal to 0, the system is considered to be a zero order system. And if the value of n equal to 1, then the system is a first order system. And if n equal to 2, then the system is a second order system. So the maximum power of s in the denominator polynomial gives the order of the system. Similarly, we can also represent this transfer function or the ratio of numerator polynomial to denominator polynomial as s plus z1 into s plus z2 into etc. up to s plus zm whole divided by s plus p1 into s plus p2 into etc. up to s plus pn. So where this z1, z2, z3, z4 etc. up to zm represents the zeros of the system. They are known as the zeros. Whereas this p1, p2, p3 etc. up to pn represents the poles of the system. So this p1, p2, p3, p4 etc. up to pn are known as the poles. So we can also define the order of the system in other words. The number of poles of the transfer function gives the order of the system. So order can also be defined as the number of poles of the transfer function. So here we can see like the poles are p1, p2, p3, p4 etc. up to pn. So the total number of poles are n. There are n poles. That means the order of this particular system is n. So with the help of this number of poles of the transfer function also we can define the order. So order is equal to the number of poles of the transfer function. So let's move on to the first order system. So now we'll see what is the response of a first order system for a unit step input as well as a ramp input. Okay. So this is how we can represent a first order system. The forward gain will be 1 by st, and we have represented a unity feedback over here. So now here we have a closed loop system. Okay, and here we need to find the closed loop transfer function C of s by R of s. R of s is the input, C of s is the output. So the overall transfer function or the overall gain is given by C of s by R of s. So in general we know that it's actually g by 1 plus gh, or if we express in a s domain, we can represent it as g of s by 1 plus g of s h of s. Right? So this is a closed loop transfer function. C of s by R of s equal to g of s by 1 plus g of s h of s, where this g of s is the gain of the system in the forward path. So here it is 1 by st. Okay, in place of g of s, here we have in our system we have 1 by st, and h of s is the feedback gain. So gain of the feedback element. Here the feedback is a unity feedback, right? We are having a a simple straight line from output back to the input. So that means the feedback is a unity feedback. So if it's a unity feedback, then h of s will be equal to 1. Okay, so now we are going to substitute those values. So we have c of s by r of s equal to, so instead of g of s we have 1 by st here, so 1 by st divided by 1 plus 1 by st into 1, so g by 1 plus gh. So now we are going to simplify this expression, 1 by st by, here we are taking the LCM, so we'll get 1 plus st by st, right? So in the numerator also it's a fraction, so there we have a st in the denominator, and in the denominator also, in that fractional part, we have a st in the numerator. Both will get cancelled, and the remaining term would be 1 by 1 plus st. So finally we got c of s by r of s equal to 1 by 1 plus st. Okay, so we are actually going to find the time response of the system. So in order to find the time response, what we need to find out is c of t. Okay, so how will you get c of t? So c of t is actually the inverse Laplace transform of this c of s. So before finding c of t, or before finding the time response, we need to find this c of s. Once we have this c of s with us, then we just need to find the inverse Laplace transform of this, which will give c of t, or the time response. So right now we have c of s by r of s with us, which is 1 by 1 plus st. Now we are going to find c of s. C of s is equal to r of s into 1 by 1 plus st. Okay, so r of s is actually the Laplace transform of the input r of t. Okay, r of s is equal to Laplace transform of r of t, where r of t is the actual input signal. So here we are going to find the time response of a first order system for unit step input. Okay, so in the title itself we have specified that the input will be a unit step input. So for unit step input, r of t is 1. The value of input is 1. So if r of t is equal to 1, then r of s, which is the Laplace transform of r of t, is 1 by s. Laplace transform of 1 is 1 by s. Okay, now we are going to substitute this value of r of s in our expression for c of s. So therefore we have c of s equal to, so already I have mentioned this, r of s into 1 by 1 plus st. Here our r of s is 1 by s. So c of s equal to 1 by s into 1 by 1 plus st. Okay. Now since here we are having the coefficient of s term as t, we are trying to make the coefficient of s term as 1. So in order to make the coefficient of this s term as 1, we need to take this t outside, right? So when we take that t outside, we will get c of s equal to 1 by s into, so t is taken outside, so that is written as 1 by t. So 1 by t by s plus 1 by t. Okay, so when we take this t outside from st, what is remaining would be s only, and here instead of 1 we will get 1 by t, because we have taken t outside. So instead of this one, 1 by t, so that is 1 by t over here. Okay, so we have c of s equal to 1 by s into 1 by t by s plus 1 by t. Now from this c of s, if we need to find the time response, we have to find c of t, which is the inverse Laplace of c of s. But if you look at this particular expression, it is not in a form where we can apply inverse Laplace transform. So we need to convert this expression to a form where we can apply inverse Laplace transform, and for that we need to apply a method known as partial fraction. Okay, so by applying partial fraction, we have this 1 by t by s into s plus 1 by t equal to, in partial fraction it can be expressed as a by s plus b by s plus 1 by t. So you need to refresh the partial fraction techniques. Okay, so a by s plus b by s plus 1 by t. So from here now we need to find the value of this a and b, right? Okay, so on the left hand side we have this 1 by t by s into s plus 1 by t, and on the right hand side, so after taking the LCM and multiplying, we have a into s plus 1 by t plus bs by s into s plus 1 by t. So for both the expressions, the denominator is same, so we can equate the numerator also. So that is the method used to find the value of a and b. So 1 by t, numerator is 1 by t. 1 by t is equated to the numerator on the right hand side, which is a into s plus 1 by t plus bs. Okay. So now putting s equal to 0 will give the value of a. So try to solve this. Putting s equal to 0, we get 1 by t equal to a into 1 by t, which will give a equal to 1 by t divided by 1 by t, and that's 1. Similarly, we need to put s equal to minus 1 by t, which will give the value of b to be minus 1. Okay, so now we need to just substitute this value of a and b in our expression for c of s. So c of s equal to 1 by s minus 1 by s plus 1 by t. This is after substituting the value of a and b. Okay, so now if you look at this expression, you can easily find out that it's easy to find the inverse Laplace transform. Now we are going to find the time response in c of t, which is L inverse of c of s. Okay, so c of t equal to L inverse of c of s, which is L inverse of 1 by s minus 1 by s plus 1 by t. So what is the inverse Laplace of 1 by s? It is 1. So 1 minus, so this is of the form 1 by s plus a. The inverse Laplace transform of 1 by s plus a is e raised to minus at. E raised to minus at. So in place of a, here we have 1 by t. So e raised to minus at is e raised to minus 1 by capital T into small t. So finally c of t equal to the inverse Laplace transform of 1 by s. It is 1. So 1 minus e raised to minus small t by capital T. Okay. Now we are just trying to draw a waveform of time response. Putting t equal to 1, then t equal to 1, t equal to 2 into t, like that. For each value of t, we'll get the c of t. And when t equal to infinity, c of t equal to 1 minus e raised to minus infinity, which is equal to 1. So our time response tend to stay at 1 as t tends to infinity. So this will be the shape of the waveform. Okay, so this is our time response. Okay.